So this is page 20 of the synchronization notes. Section 7 is another synchronization hazard or problem called starvation. So this is when a task is running, it's not deadlocked, but it's not able to get a shared resource that it needs. So task not able to get shared resource indefinitely. So there's a chance that there's a probability that it may never get what it needs to. So another way to say that is that forward progress is not guaranteed. We're going to look at another solution, a flawed solution to the Dining Philosophers, where they keep checking to see if both forks are available, and if they're not, then they just look again. We'll see how that's set up. And there's a chance that they might never see them both available. So our example is Dining Philosopher tries to pick up both forks at once, repeats if both not available. And so I'm just going to write in on this page the differences to the previous solution. So in the previous solution we had a OS mutex ID type, and this was used to represent the forks, and I used the nfill macro here, but just to keep the writing shorter and cleaner for these notes, I'll just use the number 5. So this is getting replaced with an array of Boolean variables that indicate if a fork is available or if it's ready. So we'll call it bool fork ready. We'll use 5, and we'll initialize it to true, which means that all 5 forks are available when we start the program. They're all on the table. Now this is shared data here. We're going to have multiple philosophers. Well, to be precise, we're going to have 2 philosophers checking each of those array positions. So we need to protect the accesses to the array with a mutex. So we will have one mutex, OS mutex ID type, and I'm just going to call it mutex. I'm not feeling very creative. And so a philosopher is going to examine the 2 forks that it's interested in. If they're both true, they're both ready, then we'll set them both to false. It has now picked up both forks, and it will proceed. If either of them or both of them is false, then it is going to it's not able to pick up the fork, so it's just going to loop around and try again. So the part of the code where we picked up the forks, we're going to rewrite. We're going to use a do while loop, and we need to know when we've been successful. So we are going to initialize this to false. We do not possess both forks when we start. So this part here is inside the philosopher. This is inside the philosopher function. So we're going to need maybe 8 lines, maybe a few more. So this do while not success. When we exit this loop, we will have acquired both of the forks, and the philosopher can start to eat. And at the heart of it, leave a line above this. We're going to check to see if both forks are true. So if fork ready, the fork to the the fork to the right is equal to the philosopher's ID number. So if that's true, we don't need to write equals true, because that statement evaluates to true. And the fork to their left, which we can write as fork ready, the index will be ID plus 1, except for philosopher 4, where it's fork 0, so we can just mod this by 5, and that will work. So if both of those are true, both forks are ready, we just need to set both forks to false now to tell the other philosophers hands off, those are my forks. So fork ready ID equals false, and fork ready ID plus 1 mod 5 equals false. And at this point we've picked up both forks were successful, so success equals true. We want to break out of our do while loop, and I guess I have left enough lines. So I'm missing something here. Hopefully you've noticed what it is. I'm working with the shared data, and I haven't protected those accesses with the mutex. So let's write that in. Well, okay, so let's first identify that this is a critical section because it's code that accesses shared data. And let's protect it now by acquiring the mutex before we enter the critical section. So OS mutex acquire, mutex OS wait forever, and then when we're done we need to make sure that we release it. So OS mutex release mutex. And that's to pick up fork parts, and I actually did code this and run it, and it worked. We also need to fill in the put down forks part. This part's pretty easy. You're just setting the two fork readies to false, and you don't actually need to guard this with a mutex, because we needed the mutex up here because so up here we're reading two different variables, and then based on what we've read we are modifying their values here. Even if we were just reading two different variables and needed them both to be in a consistent state, that alone would require the critical section, but reading and then modifying, that also requires a critical section. Okay, so to put down the forks, we can do fork ready ID equals true, and fork ready ID plus 1 mod 5 equals true. It's safe to do these without the mutex around them because no other task is going to be setting them to true. Like once they're false, the other tasks are leaving those forks alone, and we can release them or make them true one at a time. That's not going to make the actions of the philosophers to our left or right inconsistent or have an error in any way. So this solution has no deadlock, but starvation is possible. This could happen if one philosopher just happens to have very bad timing, so they check and one or both of the forks aren't ready. They release the mutex, they go around to the top, and by the time they acquire the mutex and check again, another task has always managed to grab one of the forks that was released since they checked, but then this other task acquires it. It's just, as a freak of timing, there is a non-zero possibility that that could happen. And that's why starvation is possible with this solution.